So then a different type of set of methods are to use, go back to our kind of decision tree approaches that we had and say we can do that. Because these methods we were talking about used the density of the space. In a sense, you could even say these ones do a little, but slightly different idea. You're talking the density of the data. Now we're going to try to isolate data points and use how hard it was to isolate them as a measure of whether it's an anomaly. And since this still relies on density, but it's a slightly different metaphor. So if you remember back to decision trees week, we had a type of decision tree called an extremely randomized tree, where we learn a tree of data. So we have our data points like usual. And we're going to learn a tree where we split on some of those data points, and kind of at every one of these now we've got some subset of points that made it here, and another side of the tree might go down further, right? So remember, in a decision tree we think a lot about like the Gini score and purity, and try to do this really well, right? And like make a split that maximizes the classification accuracy of this thing. In extremely randomized trees, it's just random. We sample from some distribution and figure out which feature to split on, and if the value is less than some other random threshold that we pick, then we go left, and if it's higher, then we put them in the right, and we have two different sets of data points, right? So we have these all being random. So why would that help for anomalies? If you think about your data set, when you've got a bunch of data points, and some of them are normal and some of them are weird, if we think about how decision trees work, right, you've got to basically cut the space into multiple sets over and over, right? And every time you make a cut, you're making a split in that set. And so if we say now it's isolation forest, the idea is we're using isolation, right? We're saying train it down. Usually we train these down until we get to some size that's reasonable, and then we stop, right? Stop if the leaf is less than or equal to some threshold. We stop and we just leave it that size because we want to build a classifier based on it. But in this one, we're going to go all the way down to 1, right? So we're really going to keep splitting every data point down the tree until we get it so that every part of the tree only has a single data point left in it, right? And you can think of it this way, that you're basically dividing up the space every time you build a split here. And so the question is, how hard is it to find a point that's isolated and is outside your data set, right? If I undo all my lines, I should have done them in that order. Some data points are harder to split than others, right? So on my very first split, I isolated this guy, right? Because he happened to be off on his own. So you could say, imagine my tree started even earlier, and this one only has a single data point in it, and he's isolated now, right? So he's done. And these points required many more splits in order to get them to be isolated, so they're way down here deep in the tree, right? So the simple idea of isolation approaches is that your depth is kind of proportional to kind of normal, right? Like normality, let's say, right? So the deeper you have to be in the tree to be fully isolated, the more normal the point is. And if you're very high up when you're split, then you must be an anomaly because it was really easy to separate you from all the other points. Right? Now that won't be true in any particular tree. Like one tree is really random. We could just randomly pick one and isolate a point that is in a big cluster of nearby points. But if we have a forest of trees and run these randomly and have like 100 of them all doing different samples, the odds are that anything that's isolated very high up most of the time is going to be an anomaly. So that's the simple idea. Basically using decision trees, but in a very simple way. So we don't even care what's in the leaves here or how many points are in them or anything. We just want to grow these trees fast and basically get these depth scores, right? So we're using this depth of the final leaf as a proxy, but then we compute an anomaly score that helps us evaluate really how much of an anomaly or normal this point is. And they use this idea of a balanced binary tree because what's the expected depth of this tree? Right. Is there any way to normalize this? So that becomes part of what they did in their paper for this. Someone has a good question. Would pure leaves be split until the size equals 1? Right? Because remember we have this idea of pure. If a leaf has all if all the data points are from the same class, or they're the same value even, right? So maybe these are ages of people in your database of COVID patients, and literally everyone in this leaf is 75 years old, so they're really exactly the same, but they're not the same persons. The data points aren't equal. But say the data points were equal, or the class label that you were looking at are equal, then you'd say that leaf is pure, right? In this case, we don't care about that. We keep splitting anyways, at least in the ideal case. You just keep splitting until there's only one left, because you want to be able to tell how hard it was to split that up from all the data points around it. Further, we're talking about anomaly detection here, so we don't even have a label. So there's no way for us to tell if the leaf is pure, because there's no label being told to us that these points all have the same something, right? Unless they're literally the same data point, and every single feature of them is exactly the same, in which case you have duplicate data, then it'd be pure. But in the purest sense, in the most ideal sense of this algorithm, you would split them regardless. You just always split all the way down to 1. Yeah, because someone was pointing out there are no labels here, right? Because we're doing anomaly detection, so you can't really tell if a leaf is pure or not. In practice, we don't always necessarily go down right to the level of spreading them down to isolated leaves points, because you don't really need to, right? What you're really looking for is this data point very high up in the tree, so it's isolated, so it's going to be an outlier, or is it very deep? So in practice, for running this, they set a threshold and they say, well, once it's beyond 10 deep or something, just stop. We don't care. But then you don't even grow the rest of the tree, you just stop. But in the ideal, like in the theory for this, you grow all the way to isolation. And the reason that we define it that way is so that we can come up with this expected height of the tree, right? Which someone else was asking as well. So this is just one way of doing it, but it seems to work fairly well to give us a score. Because what we'd like to have is a score that tells us if a data point is an anomaly or normal, right? And so they come up with this this score where yeah, I wish I had another sentence here. This is the, like, I have to look up the name of it again, but it's the pretty sure it was right, the expected depth of a balanced binary tree. And I'll have to go check that later to make sure I remember it correctly. Well, what do I mean there, right? So a binary tree, right, always has 2 data point splits around every point, right? And a balanced binary tree always has exactly 2 on every level and then stops, right? So a perfect binary tree that's balanced would be like this. And so there's a relationship between, the number of points is n, and then the depth is going to be log of n, I think, +1 or -1, I forget which it is, because you keep dividing it by 2 every time, and you're going to be, well, actually, it's log. Computer people, so it's log base 2. You're going to keep dividing it, and that's going to give you this depth of how many levels it's going to be, right? So this harmonic number gives you this measure of the depth, and I try to remember why they're adding e in there. But what this expected depth has to do with is if you're sampling random trees and growing them, how deep would you expect them to be? And so, right, so it's n minus 1. That's why we've got that there. And so it becomes a property of a random binary search tree that's got a fairly balanced kind of behavior that you're always growing it that way. What would you, on expectation, what would you expect the depth to be of some random data point, right? And so they use this to normalize the depth, so they kind of get the depth of an actual data point, x, and then they kind of divide it by cn. I have to look up the actual formula and get it after, because I thought it was on the slide already, but apparently it was taken off. Whereas, so the idea being that if the number is essentially above 0.5, then it's an anomaly, and if it's below or equal to 0.5, it's kind of normal. So that's kind of the approach they have. This could be adjusted for this threshold to be different, but they're trying to make it so that the idea of use being likelihood of reaching very deep in a tree would be low. Of course, in reality, your tree is not going to be balanced like this, so it's really just an approximation, but they use it as a way to score what a reasonable depth would be, and also to determine whether they should keep growing or not. Because once the score, for the size of data you have, once it goes beyond some level, there's no point having it being super much deeper, because basically all the points after, say, some threshold, we're going to call them normal anyways, because it's always above, like below 0.5. So you can stop actually growing to isolation. So they use this as a way to speed up the algorithm and to come up with a way to normalize it. But the essence of it still is this idea that the shallower the depth of a leaf that it ends up in, the more anomalous it is. So you could even use that number directly, but it would be this unnormalized number from 1 to n, right? So I'll put the plot up of how it works in some data sets, and while I look at what questions there were. Yeah, Hemant, hello. Yeah, I'm trying to read your question right now, so yeah, go ahead.
Can you go to previous slide?
This one?
I just want to, on 23.
Oh, okay.
The next one. I just want to know that which harmonic number we have to use to calculate the expected path length here. For specific which I value we have to select and calculate the HI for that, and then calculate the expected length. Hello?
Yeah, hello. Yeah, I'm trying to understand your question. So which harmonic number? What do you mean?
As in here it is mentioned that where HI is the ith harmonic number defined as. So I just want to know that which value we have to use for that, and then take that values for calculating the expected path length here.
Yeah, that's what I'm saying. Like the exact formula. This is part of it. I have to look up the paper and see exactly what was used in there, because I thought I had it in here already, but I guess I put a less detailed slide in.
So then we can identify whether it would be greater than 0.5 or less than or equal to 0.5. So
yeah, yeah. So it's
so that's why I asked that question.
Yeah. Yeah. So in this paper, right. Now I don't know if I can go back. No, I cannot go back. Yeah, I don't have the more exact formula right now, and if I try to draw it up, I'll find the wrong thing. So I'll post that up, or maybe continue at it tomorrow to to make sure I get the right one.
Okay.
So the main idea is this, because I also don't want to stress it too much because I don't necessarily think it's the perfect formula. It's really one way of defining this threshold. So even because we used it for some experiments and their setting of 0.5 isn't necessarily the most optimal one, but they have this theoretical way of connecting the depth to the balanced tree.
There
So
might be different harmonic numbers, right?
okay, so using different like the first harmonic and the third harmonic. Oh, I see. Yeah.
Yes. And the
Um,
fifth, it might not be useful, but one, third, and fifth would be there. So which harmonic number which
oh, I
one
see
would
what you're saying. Okay, yeah. Um, yeah, I don't remember why it's using not just harmonic. I think it's because well, I mean, you take the harmonic, the number you give it, sorry. Again, I'll have to go look at the formula and we can continue talking about it tomorrow. But the
Okay.
data point you give it is like I, how many size of n, right? So the harmonic number based on n is released by the way it's defined on the slide. So the more data points you have, how this harmonic number would be changed. But it just gives you the log. So it's saying that what's the actual depth, the expected depth of the tree with a little bit of wiggle room, given n, right? So n is the number of data points. So you're using the n minus 1th harmonic number.
Okay.
That would answer your question directly. There is one other part to the algorithm that uses this in some way, normalizes it. That's the part that's missing. So, but the harmonic number is based on the size of the data set at that point. And
Understood a bit, but it's fine. No problem.
yeah,
Okay.
great.
Okay. Thank you.
Yeah, and then there's some other element that turns this into the anomaly score. But like I said, I will have to go find the right formula and add it because I don't know where it went.
Yeah, that would be best.
Yeah. And it's already 10:30, so maybe that's where we'll stop. I'll just show this picture because then we have one other algorithm, well, two other algorithms to talk about, which I'll continue tomorrow. The way this iForest then works essentially is what you would expect. It's very good at detecting things that are outside these structures. This is from our results making it into a streaming algorithm. And so data points that are further out have been built into boxes more easily, right? You can imagine the boxes that isolate these points more easily. And basically it should be able to handle any kind of structure that a decision tree could break out. But it's being run on a bunch of trees, so it's a soft answer, right? So this is the contribution of many different trees giving you an anomaly score and then kind of averaging them together to figure out whether a point is an anomaly or not. So we'll stop there because it's 10:30, and tomorrow I'll find that final formula that makes this actually work and explain it, and then we'll go on to the other versions of this where we made one that uses Mondrian forests, which we talked about before, to basically use the same idea, and then I'll also talk about one class SVM, which is we've already kind of referred to, but there's a little bit more detail from last time. So we'll take it up from there tomorrow, and I'll try to get some answers to the other questions you guys asked. Thanks for all the great questions and your patience, and have a good day. So we were talking about isolation forests, I think that's where we ended, about this method of performing anomaly detection. And I was talking about these formulas they had, and it wasn't quite super clear. So what I had then was some other things. We just look at the papers directly. You guys are grad students, you should look at the papers directly whenever you can. So this is the original paper on the isolation forests. So 2012. Well, they had some papers before that, but this is the one where they kind of culminated it and showed all the results and stuff. So a bit more detail on those formulas. It's not that it's the most important algorithm in the world, but it serves the basis for another one, and it's kind of one of the simplest, most effective anomaly detection methods from this kind of category. Right, so we were talking about this harmonic number that gave you basically the depth, right? The harmonic number was essentially the depth of the tree based on how much data there was. But with a bit more detail on how they defined it, they're using this notion of the average length to the path to the leaves of a binary search tree. Remember we talked about that yesterday. We have a binary search tree, and that essentially this formulation, which they get from some other work, is what you'd expect the average path length from the root to the leaf of unsuccessful searches in a binary search tree. So you have a binary search tree that helps you find items or a hash table, or it's a sorted, data structure that lets you search very quickly, right? Because you just go left and right. All the values that are less are to the left, all the values that are right, higher are to the right. So it's very quick to search. You can do search in log n time with a binary search tree once it's set up. But if you are randomly searching for numbers that may or may not be in the tree, your unsuccessful searches will have a certain depth, right? So this theory, that's what this formulation comes from. It's this average kind of how deep you'd expect to get in a tree when you have unsuccessful searches. So whether that's the perfect method to use for this or not, it's a way of normalizing how deep you expect a tree to be, given a bit of noise and uncertainty, right? So they define this C value to give them this depth. If the psi is another parameter they had, so psi it was I think the number of samples. I should have checked what that was before. Oh, it's the sample. It's the subset, the training data size, right? So they have a subsampling size psi, which is how much of the data you're using. I think it's not actually a necessary part of this algorithm, but it's one of the things they use. So what's the subset of the data you're using? So essentially this is n for the purposes of this. How many data points are you actually using to train this particular tree? And so every tree you might train on 10% of the data, but it would be a random different 10% each time as part of their algorithm. C gives you this average number, and so if psi is really low, then they have these hard coding ones. If it's higher, then they give you something based on the tree. And then the score, this is the more important part, the score that they're using then is they turn that into a probability, right? So they basically do like a Boltzmann distribution, right? Where you're saying, we're going to say, what's the expected value of this height value, which is just an average, right? So they basically are computing the average value of this height amongst all the trees in their forest, right? Because they have many trees. They're going to have F trees. And C is what they're using to normalize it, right? So they have the actual depth, harmonic kind of log depth of the tree for that individual tree, and then this C becomes the normalizing agent. So all of the basically roundabout is that this gives you a nice probability measure. It's probability-like. It can be seen as a probability, because it can be 0 and 1, although it's not defining any particular distribution that we know of. And then the way they use their algorithm in terms of thresholding is that if this expected value, if the average of these depths is, what does it work? Right, so as the height of some data points, the expected one goes to 0, then your score goes higher, right? So the anomaly score is high for anomalies, right? So as it goes, because the depth, as I said before, right, if the depth is low and your data point is here versus you're going down very far into the tree, then you're saying, these points are anomalies and these ones are more normal, right? That's the idea of this iForest approach. So the highest score will be high, and then just the effect of the way they've structured this is that when the height of the trees comes out to be this actually normalizing constant, so you get essentially like uniform probability, then S will be 0.5. So essentially they have this threshold then based on the theory that if it's greater than 0.5, it's kind of an anomaly, right? And if it's less than 0.5, it's kind of normal because it's deep enough in the tree that it gets lost in this average, and the probability gets lowered. So that's the idea of how that algorithm works. And then if we saw in their paper, they had some plots showing how well it worked on different kind of weird data sets. They had ones that were a ring as well, but I guess they were doing samples on this, so it can handle, you know, irregular shapes that are in a cloud and connected to it. But yeah, it was quite, you know, useful, and it's a very fast and simple algorithm because it's learning these highly randomized trees. Right, and I had those results there already. Yeah, in that paper I did put it on Zotero, I think. Did I put it there under anomaly detection yet? But it's also in the references for the slide. So this slide has enough papers in it that at the end of the slides there are references. So that's this one. Oh, that's 2008 though. There's another one that's 2012 that will add to it. I'll add that to the slides. The 2012 one, but it's in there, the 2008 one. Okay. Okay, so that's the idea of that one. And then, let me see. Great. People sharing links too on the discussion board. Okay, so then the other, well, it's two more algorithms actually for anomaly detection, so just keep moving. This one is actually one of my algorithms. It's come from our research group. Benjamin, the TA you guys know, and some other students worked on this and got it published last year using the same idea from the iForest, and the idea of Mondrian processes that we talked about before, and combining them to basically use one that's streaming, because the iForest thing, it trains the trees all at once, and if you want to have new data keep coming in, you have to have a different data structure, so we kind of changed one to do this. So if you recall, we were talking about Mondrian processes. It was kind of doing divisions like this, where you're dividing up the space just like a decision tree, except that in a Mondrian process, if a data point is not seen, then its space isn't really divided up, right? So they do a decision tree where they actually have the min and the max bounds for data points based on what they've seen. So they only commit to saying, you know, I think there's squares in this space that I've seen, but I'm not committing to what's out here, you know, or anywhere that we haven't seen already. So it has min and max on everything rather than just less than or greater than, like decision trees do. And that means that when it gets new data, it can actually decide where this goes by expanding the tree and doing a little reorganizing, right? So it's meant to be used for classification and regression, so you do it like the normal random forest type things. At the end, you build a classifier or a predictor based on the leaves of that tree. But you could use it for unsupervised, and that's what we were trying to do. So we basically defined this tree to do streaming. So we're going to train it the normal way where data is coming in and streaming, but we're not going to try to fit it to a particular class, we're going to just use that depth idea to define an I Mondrian forest, an isolation Mondrian forest that combines both, right? And we have some results we can show. So that paper is the one where you'll find more details. It was from last year. And it didn't really do much worse than iForest in batch mode. So if all the data was ready ahead of time, iForest would work a little bit better because it can process all the data and it's actually faster. This method is definitely slower than iForest because iMondrians are a bit more complicated. But when there's streaming data, it can do much better because you can't really do that with iForest, and it did better than some other methods that could do that natively. So what was the difference? So this is the main thing, that the normal thing that Mondrian Forest already had, is that instead of when you decide to split a block, you have to decide that there's enough data to do it, right? So what it does at every point when it's deciding, it samples. Remember in the original, for some reason we switched this one to lambda, but in the original paper from last time it was tau. It's kind of like this time, right? And you say that you sample a number from this distribution as you're going, and if the number of data points you have in the new set is above that, then you decide to split, right? You have this kind of splitting time that's kind of progressing. So the longer it's been since you've seen new data points, the more likely you are to split, because probably the time has changed and data's become something relevant has happened. But you also use statistical methods to make sure that the data is going to be sufficiently large. But then we do that as well. We start, instead of growing it until the end, until we just have some sufficient size for classification, we keep growing it down to a single point, just so we do this isolation idea, so that we isolate every point until it's in its own individual box. And we build an ensemble of them, so we're building multiple Mondrian trees, just like the default algorithm. And then what do we have to do? So the path length is essentially the same. Instead of using the binary search depth tree thing, we have just the edge depth here. So we're just counting how deep it is to the bottom of that tree. And we have F trees in the forest, and we're just basically taking the average. How deep is this? So for every data point, right, because you've got a bunch of trees that have been grown now, right, and so just like you're doing normally, sorry, I should have a binary tree, but you have some new X data point, you'd apply it to all the different trees and get the actual depth, right, so wherever it ends up in the tree, that's going to give you this depth. And you're going to get that for every multiple tree, and that's what you're taking the average of. And we do the same thing as in iForest, that we basically come up with this score, the same one I showed you from the Liel paper, to give us a score of whether it's an anomaly or not. And then we can set some threshold to say if it's above this score, then it's an anomaly. So we used, in that original paper, they used 0.5. So we compared to 0.51, but we also did another one where we applied k-means to the data and then tried to figure out what a good threshold would be, right? So you could have, a bunch of data points. It always does that when I click too quickly. That's getting out of control. When you have a bunch of data points and some of them are anomalies, you could apply k-means, right, and try to come up with, clusters that they tend to fit in, and use that to figure out which ones could be anomalies. And we would set then, we tried out different values of 0.5 to see that they would kind of agree with this or not, as a quick way to kind of compare how many were anomalies or not. So there's some batch data sets that people use for anomaly detection. The one I mentioned yesterday with the network data is this, but there's a bunch of others. And these are batch, so all the data is available initially, and they tell you how many anomalies there are, so they're labeled, so you can use it as your test data to figure out if your algorithm's working well. Notice these are all pretty small, like a couple thousand. These ones get a little bigger, but you're not going to be able to do kind of deep learning stuff on these because it'd be too small, but for these things it's fine. And then we created a couple synthetic ones as well. That's what the plots we were showing for earlier were. So some of the synthetic ones are like this, where you've got, like I showed at the beginning, these different structures of points that you'd want to be able to capture. You'd hope that you could tell which points here are in the groups and which ones are kind of the noise floating around, with this one being kind of the hardest. And I guess the color here, the intensity of the black color on the background here is how high the score is. So what's the anomaly score, that S at X, for every one of these points according to the Mondrian one. So it seems to be doing pretty good. It's not really getting this spot, but that's kind of hard to get if you wanted to say that's abnormal. This one you could argue maybe it's not right. Otherwise it's doing well. So we compared then, you're doing comparative algorithms analysis, which is what you often want to do. Take those same data sets and run it on multiple algorithms and compare the results. And I don't know if these were a single run or averaged across multiple ones, but the proper way to do it right would be to say we're doing cross-validation on the data set, dividing it up, into different subsets, and then running it on those and doing comparisons. So the Mondrian forest had a little bit better structure on these kind of overlaps that had more refined division between them. So that was nice. And what was this? Okay, so then for streaming, right, so what would streaming be? You could have your synthetic data set and say, well, these points arrive in time, right? So does it change the output if the points arrive in 5 batches over time, and then you update it, right? So we were trying to compare the different algorithms on that setup and see what the difference was. Right, because one of the things that iForest, one of the things that Mondrian Forest, the original Mondrian Forest, says it's good at is that it's good for streaming because it can do regression and classification models based on streaming input, but they claim that the models that it learns during streaming are no worse than it would learn from batch, and the original Mondrian Forest paper has analysis on that, right? So they take all the data and just learn the thing from scratch with no streaming and come up with accuracy scores and F-score and AUC curves, and then they train it as batch and give it the data coming in incremental kind of waves, and then compare it. And they show that it works just as well, which is a good thing, right? Because you could expect that a batch method would be better because it's focused on all the data at once. So for anomaly detection, people often report the AUC score, right? And if we remember what that is, we have our ROC curve, right? Where we're talking about this true positive rate and false positive rate. You can check that. I could possibly have got those reversed. I hate when that pops up. That's so annoying. You got your ROC curve, right? And that you're saying you're changing some value, right? So for anomaly detection like this, we have the perfect thing here because we've got this threshold. So it's very well fitted. Anomaly detection is very well fitted for ROC curve analysis and the AUC score, because we got a threshold and we're saying, well, if in our case for this algorithm, right, we're saying if X is above this threshold, then it's an anomaly, right? And in the case of iForest, we set this threshold to 0.5, but you could range it over all of them, right? So you could have the threshold being 0.2, being 0.3, being 0.35, and ranging through all the values. And then you'd get this curve. And remember, the AUC is just the area. That's what it stands for, area under the curve. It's the area of this, right? And AUC of 1 means you're perfect because you never got anything you didn't make any errors, right? You didn't detect something that was normal, we'll call it an anomaly, and you didn't miss any anomalies. That would be a perfect score that fills the entire plot, right? And this ROC curve goes from 0 to 1. So it's a very good kind of measure for a lot of these, if you have a threshold-based algorithm, which anomalies things often are, to compare. And as far as I remember, obviously we had better scores than some other ones, so it was higher. And SVM's the one, LOF we talked about yesterday. SVM's the one we're going to talk about next. But on some data sets, these things work quite well. On some data sets, I4S beat us, so this network one, there's the blender again. And different results we're reporting here. And more results. Some of these I think interesting about that. Yeah, so for this one, we were, in terms of speed, it's slower because it's doing quite a lot of analysis. So it's not as slow. It's it's faster than the ones based on PCA because those ones had to basically run PCA on all the data. But it was slower than the other methods like iForest, which grow very fast sets of trees. Yeah, so that was the result of that algorithm. And I have a plot later which has all the comparison of all the different algorithms on those synthetic data sets we have, which I'll show that after we do the one class SVM. One more question slipped on slide 33. That's further back. Yeah. So it's slide 29 in mine. Counts the lower and upper, right? Yeah, it's the lower and upper bounds because in Mondrian forest you have the lower and upper bound for every data point for where you'd split in the tree to define that. So every split in the tree has a lower and an upper bound, and so when you apply a set of data points to it, you'd figure out which data points go to the left and which go to the right based on that. But it gives you the range of that block. Yeah, because XB here is a block of points that happen to be in a leaf node. Yeah, so for every leaf node XB, it has an upper and lower bound on each of the features, and it's a vector because it has it defined over all the features that got you there. So it really defines that rectangle in the hyperrectangle in the feature space. Cool. Good. That's a good question.